Okay, continuing with work and kinetic energy problems. Here's another one. And so you see, we can solve for different things. Like so far, we've solved for displacement in the last two. This one, we're going to be solving for net force. So we've got a bobsled. It's pushed along the surface by two athletes. It's pushed a distance of 4.5 meters starting from rest. And at that point, its speed is 6 meters per second. We want to find the magnitude of the net force. Okay. So here we're given displacement. We are starting from rest. So our initial velocity is 0. Our final velocity is 6 meters per second. We're given the mass, and we just got to solve for the net force. So we're putting everything into this equation. Net force times displacement equals 1/2 mvf squared minus 1/2 mvi squared. This is my change in kinetic energy. And I know this is 0 because it said I started from rest. I know this is 6. So I'm filling these values in here, filling my displacement in because they said they pushed it 4.5 meters. And when I plug all that in, I solve for it and I get 300 newtons is the net force that they're pushing it with, and that would be minus if there's any friction. They don't really say anything about friction here. So, okay, so there we solved for F net instead of displacement. But velocity is another thing you could solve for, maybe even mass. But this is one of those tools where you're setting stuff equal to each other, and then you can solve for quantities that you're missing, like we did with conservation of energy. Okay. Okay, and then here's another one. Now we're going to solve for our final velocity. We've got a grocery cart. It's pushed 412 meters along an aisle by a shopper who exerts a horizontal force of 40 newtons. We're not worrying about friction. The cart starts from rest. What is its final speed? Okay, so here they tell us the weight of the grocery cart, so we can use that to solve for mass. Remember, weight, also your force of gravity, is m times g. So I just divide 98 by 9.8. I get 10 kilograms there. And then I'm going to again use the same equation. F net times displacement is my change in kinetic energy. I know my initial was 0. So see, this is another one where a lot of times you'll have terms that simplify because you're starting from rest. Or you could be ending at rest if there's like a net external force slowing something down, maybe. But anyway, so this means my initial velocity is 0. I'm solving for my final velocity. And I'm given my net force, I'm given my displacement, and then I just figured out my mass from the weight that I was given. So again, put everything in. 40 times 12 equals 1/2 mv squared. Simplify all these numbers out. V squared is 96, and I got to take the square root of that. That is not my final answer. This is my final answer, 9.8 meters per second. Funny, we've seen that number a million times. That's just a coincidence, but anyway, so that's another example of work and kinetic energy theorem where you're solving for some kind of quantity. Okay, we've got somebody did an experiment, and so they graphed an applied force exerted on an object versus the distance it traveled across a horizontal surface. They've got this graph. They want to know how can they use the graph to determine the work done by the applied force. So remember, we talked about this graph for a day. We made these graphs with force sensors. We know that force times displacement is work. So if we take the area bound by the line of best fit, that should give us work. So we'd have to get like a best fit line of these data points and then take that area. Okay. Anything else is not going to give us work. Like maximum value of the applied force is not going to give us work because this is a changing force, right? So that's one of the reasons that we can use the graph is to pick up like that line of best fit. Okay, we don't just want to pick one point. Multiply weight by the total distance. That would mean force of gravity would be the force acting here, and we don't know that. It says an applied force. We don't know what the force is. Also, it's traveling across a horizontal surface, so that doesn't really make sense. And then slope doesn't really make sense because that wouldn't give us what's going to give us work is the area, because that's going to give us our force times our displacement. Okay. So this is one of those important graphs to remember, like why it's important. And it's because the area under the curve gives us work. Okay. All right. Power. Got a few on power. So this one goes back to the lawnmower question where we got our work was 1,000 joules from pushing the lawnmower. This one. Okay. So now we're saying that we covered that distance in 5 minutes. So what is our power output? Okay, so we already calculated work. Power is work divided by time. Okay, it's your rate of work done or your rate of energy transformation. So I just need to convert 5 minutes into seconds. So I'm going to do that over here real quick. 1 minute is 60 seconds. So that gives me 300 seconds, and then I divide 1,000 by 300 and I get like 3.33 watts. So that's my closest number. Remember, watts is the unit of power. Okay. And power, like I said, is really simple. You're really just taking work that you've calculated and dividing by time. You can use it to help you get other things. This one I thought was interesting. So we've got a crane that has a power of 600 watts. I know that because of the units. It lifts a bucket of rocks to a height of 11 meters in 6 seconds. And what is the mass of the bucket of rocks? So imagine it's like this giant crane, okay, lifting this huge bucket of rocks. And it's going to lift it 11 meters, okay? When you're lifting, we talked about this when we did the lab with the stairs, your force is the force of gravity, okay, or the weight, because that's what you're overcoming to lift something. So our work in this case is going to be our mass times g times our displacement. We're trying to solve for mass, okay? So we've really, as we put this together, we've really got everything else. We've got power is 600 watts. We know that work is going to be 600 times T if we're solving for work. And then within work, we're actually going to be solving for mass. So we set work, M times G times D, equal to power times time. Okay, so I'm really taking these two equations, kind of manipulating this one to solve for work, and then putting this in for work, because I know everything except for mass. Okay, I know power, I know time, I know G, I know displacement. And then I solve it out and I get 33.4 kilograms for the mass. Okay. Okay. And then there's one more quick one I think I can do. This one kind of goes back to the stairs lab. We want the power exerted by a student who's climbing stairs. So we've got their mass, we've got the height of the stairs. It takes them 15 seconds to climb them. So we're going to get their work as M times G times D. Again, that's the same as what we just used here. Okay. Work when you're lifting is our weight. That's our force. Okay. And you're really like lifting yourself as you're climbing the stairs. So work divided by the 15 seconds gives me 170 watts. Okay, so that's all the homework.